Hi class, today we're going to be discussing energy and chemical reactions. So in almost every reaction, it involves a loss of heat or a gain of energy. If it's a loss of heat, it is lower in energy than what the reactants were, and if it takes energy in, then it needs that energy in order for the chemical reaction to occur. So we're going to visit back to something that you learned in chapter 3, which is the joule. That is the SI unit for energy. So we're dealing with energy here, but it's usually we deal with joules for heat. So we either deal with joules or kilojoules, and these are conversion. This is a conversion you should definitely know. 1 kilojoule equals 1,000 joules. So the heat of reaction is the amount of heat absorbed or released during a reaction that takes place at constant pressure. The change in energy occurs when reactants interact, bonds break apart, products are formed. The heat of reaction is symbol delta H, is the difference in energy of the products and the reactants. So let me explain what's going on with this slide. Every chemical reaction will either give off heat or, well, let's just say every chemical reactions either give off heat or absorb energy. Give off energy or absorb energy. And this occurs because the reactants are interacting, bonds are breaking, and then in order to have products, new bonds are being formed. So what we're going to look at here is this bottom portion are the products minus subtracting the reactants. Is this going to be a negative or a positive, which will mean it'll be an endothermic or exothermic reaction. So in an exothermic reaction, that's heat is given off. Heat is released. The energy of the products is less than the energy of the reactants. Heat is a product. So in this case, the reactants are higher in energy. That's why they're higher up here. And as the chemical reaction occurs, that heat, that difference of negative 185 kilojoules is released from this reaction in order for the products to occur. It has to release that energy for the products to be produced. So this difference from here to here is this amount of energy that's being released during this reaction. So bonds are broken from these reactants, and new products are formed, which means new bonds are formed. In an endothermic reaction, it's the opposite. Heat is absorbed. The energy of the products is greater than the energy of the reactants. Heat needs to be added into it for this to occur, and it's a plus sign. So the reactants are actually lower energy. So for this reaction to occur, it needs energy. The energy will push this reaction to occur, force these bonds to be broken, and new bonds to be formed. So the energy has to go in or this reaction will not occur. And that means it's a plus. And the difference with these is that you see on the product side, this 185 kilojoules is on the product side, and that's an exothermic. And an endothermic, it's on the reactant side. It needs that energy to get this reaction to go. The value of delta H refers to the heat change for each subject in the balanced equation. So for the decomposition reaction, we take a look at, we have water that decomposes to hydrogen gas and oxygen gas. So that is a total of 572 kilojoules is the heat of change or heat of reaction that is produced. This is a plus, so it's an endothermic reaction. It needs that energy in order to push the water back into its natural elements. Here we have water, and this is 572. So remember, it's an endothermic, so it's going to be with the reactant side and not on the product side. That would make it an exothermic reaction. Now, knowing this is where it might be a little confusing, but it actually is not a big deal from anything you've learned this section. This 572 is representative of any element here. That means that 572 equals 2 moles of water, 572 equals 2 moles of hydrogen, and 572 equals 1 mole of oxygen. It applies to everything in this balanced equation. And now we're going to use it. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? Now let's look at this problem. We only have one amount to start with. It's asking about how much heat has been released. So it's an exothermic, and we can see here from delta H it's a negative. Now this means that it is negative 92.2 kilojoules for 1 mole of nitrogen, negative 92.2 kilojoules per 3 moles of hydrogen, and negative 92.2 kilojoules for 2 moles of ammonia. So we want to know how much heat is being released. We're given 50 grams. heat released in kilojoules. We know how much heat is given off in this reaction, and we are going to base this on the equation. So we have grams, and we need to get from grams that's been given to us to joules. Heat, how much heat? Heat is the key word in kilojoules. So we need to get from grams to joules. How do we do that? Well, first we need to get out of grams. We never work with grams. We need molar mass. So we have to get to moles of ammonia. And then from there, the heat of reaction. We can set this up with this number and which one of these elements we need, and that will give us kilojoules. So let's look at what we need. We need ammonia. So 1 mole of ammonia equals 17.03 grams of ammonia, and we can set that up as a conversion factor. And now we can take this amount and use this as well. So 2 moles of ammonia equals negative 92.2 kilojoules, and we can set that up as a conversion factor. And now we just use it. So 50 grams of ammonia, set up the molar mass. The moles of ammonia, grams of ammonia cancel out. The moles of ammonia will cancel out once we take the 2 moles of ammonia here and we use the amount that's given to us, and that will cancel out the moles and leave us in kilojoules. So this is not a difficult problem. It means that this amount is for this amount's for this is amount for this. It's very straightforward if you remember that you can use it for any of these, and you set it up the same way we've been doing other ones. So don't let this new information trip you up. It's not really anything you haven't already been doing. Okay? And here is a kind of a map so you can see everything that we've been covering, and you can go over it. Now, this is oxidation reduction is the one that we didn't cover. So, but everything else you can see that we have.